Alright, hello everybody. Welcome back to another coding until I get an embedded internship video. So today's going to be a short video. Unfortunately, it's 9:45, which is pretty late for me. So I'm not gonna do much stuff today. Other than that, so I probably won't be doing much microcontroller stuff today. I will look at my YouTube channel. I covered a lot of key topics in embedded. I think I will probably look at the roadmap right now. Let me give me 1 second. Okay, so let's open this up. Hold on. Okay, so good. All right, so oh, okay, sorry about that. Okay, so what do we gotta do now? We covered a lot of the key features on the ESP32 on ESP-IDF. I think I know most of the stuff. The only thing that I don't know really is testing and OS stuff, OS operating system stuff, which I think is very important. But I'm going to learn that in school, so I don't think I'm going to do that right now. The soft skills, that's more other stuff. Electronics, this I learned in school, so I don't need to worry about that. Oscilloscope, multimeter. UART, iCrisp, we definitely cover that in this channel. So yeah, I guess we can move on to, we can like do a little bit of algorithms and stuff, maybe. The thing is, algorithm and data structure is literally just like leak coding. Like, there's not much fun in that. Like, I could show you algorithm and data structure, but that would just be me solving leak code questions all day, which I would rather not do right now. So yeah. We could either continue with USB, or we could do other stuff. What about the embedded wiki? this internet protocol. DMA works. Risk V, so we can cover risk V as well. Instruction set architecture. Yep, reduce instruction set architecture. ARM cores, processor pipelines, fixed point math. There's no way this is a real question. Okay, so a lot of the stuff seemed like very obscure. But I guess if it's asked in interview, I guess we should probably learn it. Lots of logic voltages, logic families. Okay, no, I'm not too sure about that. So yeah, not much to do here. We should probably do the projects. Well, I guess if there's nothing else to do, design patterns. Look at design patterns here. State machines? This is more digital stuff, hardcore digital stuff. Yeah, that's for later. I think what I'm going to do right now is the bit manipulation exercises. There's a good video out there. This guy. So I think this guy makes a lot of good content on embedded systems. Bitwise.
Hi, I'm Marit. Now that I use
RHTO, I've heard of that guy. Bit manipulation play. This is a good series. Let me watch this actually.
All the secret. So finally, we will be starting off with the bit manipulation playlist. Before that, if you're welcome back to the channel. I hope you guys are doing 2 into 1 will be 2, right? And
What's up? Okay, we're right back. I'm gonna get my tablet.
the conversion, 1s and 2s complement. So first of all, let's understand one thing. You must have done this in your school time. Now if I write something as 7
Okay, hold on.
to the base 10, This means the number is in decimal format. If I ask you, can you convert this into its binary equivalent, that is basically the number in its binary format, that is base 2? How can we do that? It's a very easy thing. You must have done it in your school days. What we do is we take 7 and we divide it by 2. Whatever is the remainder, we write it. So the remainder is 1 because 2 into 3 is 6 and there is a remainder of 1. So 2 into 3 is 6. So we write 3. Again we take 2 and we divide it. So again if I divide the remainder.
Okay, so this is some basic stuff. So yeah, if there is a remainder, but it's 1, if they're not, then it's a 0.
Remainder will be 1.
Yeah.
So this time
So we're just taking a modulus here.
two into 1 will be 2, right? So this then I get copy, we will take both.
Yep, perfect. Really not much. This is like, you know, you
In decimal. Got it? Let's take one more example.
let me skip this. Skip.
Just skip this, right? And you move on to the left. And the indexing goes as 0,
This
1.
yeah, and then this is converting back between 2 is very straightforward. This is just going to be good. So there you go. Easy stuff. We learned this in university. Let me skip.
After division, what am I doing? I'm picking up these remainders and I'm going from bottom to up. So maybe while the division happens, I can store the remainders. I can. So I'll take a res and I'll initialize it empty. It's a string. And what I'll do is I'll say, hey, if
That stuff.
n modulo 2 equal to 1, that means on division if it leaves a remainder of 1, I will say resultant, can you add yourself a 1, right? Or else a resultant.
What's the formula? What's the formal term for
What will
this?
happen if I do this? In this case, first one will get attached, then this 0, then this 1, then this 1. So you'll get something like this, which is not what you want. You want it in the reverse manner. Reverse manner, yes. So please make sure after the while loop is completed, reverse the resulting string, and once you've done it, you can return this resultant. Done and dusted. This is a function which is gonna take any possible integer. It's gonna give you its binary equivalent in the format of a string. You can do it in terms of list or any of the data types or data structure as you wish to. So what is the time complexity? Can I analyze the time complexity? It's very simple. I'm dividing it by 2, dividing it by 2. If you would have seen my binary search videos, you know, right? Logarithmic base 2n. When you divide it by 2, it's always logarithmic base 2n. Got it? What about the space complexity? It's again logarithmic base 2n. Why? Because the number of steps I'm taking, the number of remainders will be same. Whatever number of steps I'm taking, the number of remainders will be same, and that is the space that this resultant string will take, right? 4. Quite simple. So this will be the time complexity, and the space complexity we are looking forward to convert at decimal
Okay, cool.
to a binary. Try to try out the reverse one as well, that is converting the binary to its decimal equivalent. Which is
Okay, that's cool.
My best.
Oh my god. Okay, so yeah, fairly basic stuff. We learned this in university. I don't think we need to go too much in depth into this.
Let's understand one thing. When I write something as int x equal to 13, does the computer really store 13? doesn't. Why? Because the computer only understands
Binary.
and 0, right? It doesn't understand something like 13. So what happens behind the scenes is this 13 is converted into its decimal equivalent, which is 1101. That is the decimal equivalent. It doesn't store 1101 base 2. No, it doesn't. Why? Because there is something as integer. Whenever you write something as integer, it means 32 bits. The computer stores 32 bits in its memory.
Yep.
But this is nothing but 4 bits. What about the other 28 bits? What happens is
These are all
they
zeros.
fill themselves up
Yep.
with zeros. So this is the rest 28 bits. So overall the computer stores this one. Yes, this is what the computer stores in its memory because it only understands 1 and 0. Now whenever you're trying to read x, assume you say print of x. Why is 13 getting printed? What happens is the reverse conversion happens. It gets converted into the decimal and then it is printed. The computer never stores the decimal, always converts the number into the binary and then stores it. Remember this. Now you might be thinking, okay, integer is 32 bits. What about the other? So long is 64.
Yeah.
So I won't be going for long because most of the problems you can solve it with int, and whatever concepts I'll be teaching with integer, and they can be applied to long as well. It can be just extended.
Okay.
The concepts are same. The only difference will be 62 bits. I'll be teaching in terms of 32 bits. You can extend it and apply it to 64 bits as well. So before getting into the bitwise operators and the problems, we're learning about 2 more concepts. Again, it won't be required in problem solving, but it is just good to know. The first one is ones complement. Imagine I give you a number 30 and ask you, hey, what's the ones complement of 30? So what you do is you basically write it in terms of binary. 1101 is the binary. Once you've written that, you convert that. Like you flip all the bits. Yes, you'll be flipping all the bits. So once you flip all the bits, you have something like 0, 0, 1, 0 in terms of binary. And this is your ones complement. Got it? Now, first complement is super simple.
Once that's okay. And of course that's just gonna be your signed one. Yeah, so it's gonna be,
Let's get one of two
and you add one for 2's complement. Now we learned this in school. Don't need to review this. This is it's gonna be 0011, which is pretty cool. Obviously, this is how you find the difference between like signed and unsigned.
So what do you
Yeah,
just as of now,
yeah.
not
So that's gonna be your unsigned, right?
And next time we'll be teaching about the addition operator, whether you understand the rules as well.
Yeah.
So this is your 2's complement. Very simple. Figure out the 1's complement, add a 1, get the 2's complement. Super simple. Got it? So we need to learn about the operators that we will be using in bitwise manipulation. Why? Because without operators, you cannot solve.
I didn't know. Shoot! But I didn't know that like the 1's complement is a. I guess that's why they call 2's complement, right? That's the second step. I didn't know the thing, the flipping the bits was called the 1's complement, but that's interesting.
So let's get started, and I'll be starting off with the AND operator.
Okay, yeah. Again, we learned this in school. Anybody who's taken a digital design course will learn this in school.
Simple. AND operator, probably I'll just start over here. AND operator means all true means true, one false means false. Remember this. What does this mean? So if I write something as x equal to 13 and 7. So what happens in the background is 13 is converted into its binary, which is 1, 1, 0, 1. Again, 32 bits because it is integer, so you'll always have 0, 0, 0, something like that. But I will not be writing it because zeros, they don't come into picture that much. What is 7? 7 is 1, 1, 1. That is 7 if you try to convert it into binary. Again, 0, 0, 0, 0, 0. Around 29 bits of zeros. So you do an AND with it. So again, you can fill this with 0 because there's nothing. So when I say all true, all means in this particular row, there might be another number 9. There might be 4 numbers that you're doing AND with. Whatever, if there is one way out, all has to be, like all of them has to be 1. Then only you can write 1. So both of them are 1, so I write 1, right? Over here, there's 1 false means a none, and the 0. 0 means false, basically. Over here, all of them are 1. 1 means true, yes. Super hydration keeps me.
Why does YouTube have so many ads, bro? Like, I'm just trying to watch in peace.
Again, all of these will be 0.
Yeah, so again, this is bitwise, so you just and all the bits. Yeah, not much to cover here.
And what is this number? This is nothing but 5, yes? So the result that you'll be getting is 5, and you do an AND operation. I hope you've got the AND operator. So AND operator is done. The next one is OR operator. When I say OR, it means 1 true means true. All false means false. Got it? So when I say x equal to 17, the sign of OR is this one. So 5. 17 or rather let's say 13. 13, 5, 7. So again 13's binary is 1, 1, 0, 1. 7's binary is 1, 1, 1. So when you do an OR, so let's do an OR. So when you do an OR, which is basically 5 operator, 1, you at least have 1 2, right? So you at least have 1 2. You at least have 1 2. Over here is a 0. You at least have 1 2. And the remaining bits are 0, so you don't care about that, right? So this is your equivalent. And how much is that? Quite simple. This is 1, this is 2, this is 4, and this is 8. 8 plus 4, 12 plus 2. What do you
XOR.
OR operator is clear, right? So the next one, ZOR. So let's understand the ZOR operator. So ZOR operator is very simple. If you have number of ones as odd, you'll always get 1. If the number of ones are even, you'll always get it as 0. Remember this. So if I say x equal to 13, the symbol of ZOR is this. 7. 13 is 1, 1, 0, 1. 7 is 1, 1, 1. And if I do a ZOR, which is this, how many ones are there? 2, which is even. So this will become 0. How many ones are there? 1, which is odd. So this will become 1. How many ones are there? Oh my bad. This will be again 0. If this is 0, this is going to be 1 because odd. And over here, there are 0 ones. The 0 ones means even ones. Again 0. Technically all will be 0. But this is the number that you will get. And what is the value? The value is 10 because we try to convert this into its decimal. This is 2, this is 8, and rest of all are 0, so 8 plus 2 will be 10.
If they're the same, 0. If they're not the same, 1. Simple.
10 is what we will take. So Dammnit is all of it.
But
as well. The next one is shift. So Dammnit is all operator. Now it's time to understand the shift operators. So let's start with the first shift operator, that is the right shift operator. There's one more, that is the left shift operator. We'll come to that afterwards.
very important.
X equal to 13 right shift of 1. So this is the symbol of right shift. If you write something as 13 right shift of 1, you can write it 2, you can write it 3. What does it mean? 13 means 1, 1, 0, 1. That is in binary. And there are zeros. Right? Lots, 28 zeros on there. So when I say right shift by 1, it means this one goes off the cliff. Yes, this will go off the cliff. And this 0 will be here. This one will be here. This one will be here. What about the rest? There were zeros, right? Again, this 0 will be here. This 0 will come here. So technically, there are all zeros over here. So this is what happens. This is what happens. And what is this number? This number is nothing but 6. So you get something as 6. Keep this in mind. It is going to be helpful as we move forward. Let's do one more thing. Let's say x equal to 13 right shift of 2. Okay? So again, that's 1, 1, 0, 1. When I say right shift like 2, this will go off the cliff and this will go off the cliff. 2 places. So this will come to the right. This will come over here. This 0 will come over here. This 0 will come over here. Again, this will be written with zeros. So what's this number? This number is 3. Again, keep it in mind that this number is 3. I can probably say x equal to 13 right shift of 4 as well. I can say that as well. So if I say that, what will happen? I have something as 1, 1, 0, 1. How many will go off the cliff? All of them. All of them. And this 0 will be here, this 0 will be here, this 0 will be here, and this 0 will be here, and then continue. So it will be 0 technically. You're getting how the right shift works, right? So there is a very simple formula to get this value. It's very, very simple. So if I say 13, or if I say by that reason x, right shift by any number k, it basically means x divided by 2 to the power k. Yes, that is how the formula is. And I can prove it. I'll give you the 2 as well. Before that, let's work on this. So 13 divided by 2 to the power 1, which is 6, right? 13 by 2 is 6. 13 divided by 2 to the power 2, that's basically 13 by 4, that's 3. 13 divided by 2 to the power 4, which is 13 divided by 16, which is 0. Works. Why does it work? So I take a very small example. This one in order to explain why does it work. So I'm saying 13 right shift of 1. Let's understand what is 13 initially. 13 is 1, 1, 0, 1. Let's try to write down it in terms of the decimal conversion. That's 1 into 2 to the power 3. That's 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. Agreed? Agreed too. So when I say 13 right shift of 1, what is the number that I get? Or rather, what is the binary that I get? 1, 1, 0. So let's try to write it as 1, 1, 0 because the 0 will be here, this 1 will be here, and this 1 will be here. This is what we get. And what happens is this one, like this one, which is initially here, now comes one place to the right. Thereby, it ends up being 1 into the power 2 plus 1 into the power 1 plus 0 into the power 0. this happens, right? And this is off, this is off, this is off the cliff. So technically this is off the cliff, right? And this number is same, this number is same, this number is same. What has changed? You see something, 3 is 2. Technically if I just take 1 2 out of it, 1 2 out of it, like this. That is why if you're doing one right shift, okay, divided by
is this what it's called? No, this is something else. Sorry about that. Sorry about that.
Where to the bottom. Got it? So we have done with the right shift operator. And there's one more shift operator, that is the left shift operator. But before that, one thing. When I write something as x equal to 13, the computer stores it in terms of 1101. A simple binary because it's a positive number. So what happens when I write something as x equal to minus 13?
It's signed.
How does the computer store this particular positive thing? We know this as well.
If it's 1, it's signed.
That integer has 32 bits. Remember one thing, the first bit or the last vector, if you talk about from left to right, is basically the 31st bit. That is reserved for sign. That is reserved for sign. And the rest are used to store numbers. Like in this case, it will be 0, 0, 0, and then 1, 1, 0, and 1. This is how I will be storing 13. What will be the sign? It's very simple. 0 for positive, 1 for negative. So what happens is, I say 0 over here. So this is a sign bit, and the rest are used for storing numbers. Okay, fine. What about x equal to minus 13? How does the computer store it? Very simple. 2's complement. Remember that? We're going to use that way. So when I say minus 13, okay, what we do at the first step is, we write down the simple plain positive number 13, which is basically starting from 0, goes on till 1, 1, 0, 1. So we write down the plain positive number. Now whenever the computer has to store a negative number within itself, it converts it into its 2's complement. So we'll be converting this into its 2's complement. What will be it? You know, first step is 1's complement, which is flipping all the bits. It's going to be 1, 1, 1, all 1's, 0, 0, 1, and 0. So 1's complement is done. Once 1's complement is done, you add a plus 1 to it. So once you add plus 1 to it, what happens is, you get 1, 1, 0, 0, and these all are 1's. And the last bit is also 1. And the last bit is also 1 because of the flip that you did. The last bit is also 1. So this will tell you that this is a negative number. And this is how it understands that if it is storing 2's complement, it means that it's storing a negative number. So this is what will be stored internally. Got this? So I know how to store a negative number as well. So very simple question. What is the largest integer?
Bro, this is the third ad in the same video. And it's a double ad too. God, like, I don't understand YouTube, bro. Okay, it's not a double ad, thank you.
So can I say the last one is reserved for sign, right? So it will be 0 for sure, because 0 means positive. If I try to fill all these with zeros, will it make sense? Then the overall number will be 0. Doesn't make sense, right? So can I say this? Can I say this that, okay, probably I can have 1, 1, and all filled with 1s, yes, which is technically nothing but 2 to the power 30 plus 2 to the power 29 plus 2 to the power 28 and so on to 2 to the power 0. Can I say this? I can, which is nothing but 2 to the power 31 minus 1. So this is the largest possible value that you can store in an integer. And this is technically, like, you might have seen this integer max. This is this value integer. So the next question, what will be the smallest number that it can store? And you might ask this last bit, all ones. There is nothing but operator. Flip it. So if you flip, the sign will flip to 1. This will be 1, 1, 1, 0, 1, 0. Okay. Flip is done. Now what is the next thing? Check negative. Is it negative? It is negative. If it is negative, convert this to its 2's complement. Well, it's a negative number. You already know it's a negative number. Convert it into its 2's complement.
Yeah, of course not. It's just, you just reverse the bits. Not will just mean to reverse all the bits. Okay. So yeah, so that's the first video done. So yeah, that's fairly basic stuff. I feel like every university student learns that in the classroom. So this.
6, we will be having 5. How can I do it? It's very simple. I can say, I take a third variable temp, I'll store the value of 8 into it. So temporary will be having the value 5 initially when we start with this state. Done. After that I say, okay, A equal to B. So I take the value of B, which is 6, and I put it into E. After that I say B equal to, can I say B equal to A? I cannot. Why? Because if I say B equal to A, A's value is 6, so B will still stay as 6. This is the reason I put the third variable temporary. So basically I say B equal to 10, B will be taking the value 5, so it'll be 5, done and dusted. But over here, I'm using the third variable. Now in an interview, the interviewer might ask you, can you solve this without using the third variable? But that is where the XOR operator will come. Now what is the XOR operator? Quick recap. Now the P will be split into, I can say, I take a third variable temp, I'll store the value, yes, and the first problem will be swap two numbers. So the problem statement is swap two numbers. So you'll be given two numbers, A and B. So assume A is given as 5, B is given as 6. Now your task is to swap them. So after swapping, A will be having 6, B will be having 5. How can I do it? It's very simple. I can say, I take a third variable temp, I'll store the value of A into it. So temporary will be having the value 5 initially when we start with this state. Done. After that I say, okay, A equal to B. So I take the value of B, which is 6, and I put it into A. After that I say B equal to, can I say B equal to A? I cannot. Why? Because if I say B equal to A, A's value is 6, so B will still stay as 6. This is the reason I put the third variable temporary. So basically I'll say B equal to 10, B will be taking the value 5, so it'll be 5, done and dusted. But over here, I'm using the third variable. Now in an interview, the interviewer might ask you, can you solve this without using the third variable? But that is where the XOR operator will come in. And what is the XOR operator? Quick recap, even number of ones will be 0, odd number of ones will be 1. Can I say that if I XOR two same numbers, 5 XOR 5, the value will be 0. Why? Because 5 is 1, 0, 1 in binary, and again 5 is 1, 0, 1 in binary. And doing this OR, since they are same numbers, every row will have even number of ones, and wherever there is 0, there will be even number of ones, that is 0 number of ones. So everything will be 0, 0, 0. So thereby, XOR of same numbers will be 0. So I will be using the XOR operator in order to stack two numbers. Let us see how. So what I'll write is A equal to A is over B, and this will be my step number 1. After this, I'll write B equal to A is over B again, right? So write this, what will happen is, this A, what is the value of this A? Can I say this much? It is, because this is what I did in step 1. So I can write A is over B is what A is, and then is over B. Now what is B is over B? It is 0. So eventually, B is equal to A. Agreed or no? Agreed?
Oh,
After this, I'll write A equal to
that's very
A is over
smart.
B. Tell me one thing, what is the value of A?
So yeah, if A equals A XOR B,
The value of A is this much, right? So write this again. A is over B. Is over
Yeah.
B. This time what is the value of B? It's 8. Where is 8, right? So I can just write it as A. It is not B anymore. It is A. So A is over A will go off as 0, and eventually you will be left out with B. So you see what we did. It was B equal to A equal to B. The XOR operation will do it for you. So this is how you can easily extract. So it's very simple, 3 lines, and you can easily extract two numbers without using the third variable. So time for the next problem, which is check if the ith bit is set or not. So what is the problem stating? It's stating that you will give it a value n, imagine 13, and you will give it a value I, imagine 2. And your task is to check if these.
sorry. Anyway, yeah, okay, so yeah, so I think we might go through this playlist as time goes on. It seems like a pretty useful playlist. Apparently these are interview questions they might ask you, so I think it's definitely worth going over.
Why wait?
So yeah, this stuff we also need to go over sometime in the future.
Element. So if you carefully look, this does. Let's start the loop. Okay, if the
All the same.
Let's discuss the ultimate roadmap.
Okay, sorry. Okay, anyway. So yeah, alright guys, thank you for watching this video. I'll see you guys next time. See you.